Okay, so today we're going to study center of gravity's effect on robots, specifically how they turn and how they tip. Now, we talked about turning a little bit, well, actually a lot bit, on the last lesson, and we're going to continue it a little bit more and clarify a couple of things that hopefully will make it, well, a little clearer how this affects robot turning. So for starters, I just want you to find the centroid of the following object. You can ignore the weight of the wheels. We just have 100 pounds on this side and 50 pounds on this side. Go ahead, pause the video, and resume once you're done. Okay, now that you're done, it should be pretty easy to find the center of gravity of this object, especially in the x direction, because, well, there's symmetry here. So our center of gravity in the x direction is just going to be halfway along this. So 1, 2, 3, 4, 5, 6, 7, 8. It's going to be 1, 2, 3, 4 units in right here. So our center of gravity in the x direction is 4 inches. Center of gravity in the y direction is going to equal. So for the y direction, before we do any calculations, we should know that the center of gravity is going to tend more towards this side of the robot because there's more weight on this side of the robot. So our center of gravity is always going to be on the side with more weight on it. So we'll do the calculations starting from this point. So we'll do 50 pounds times, where's the center of 50 pounds away from here? Okay, so that's right there. It's 1, 2, 3 units, 3 inches, plus 100 pounds times 1, 2, 3, 4, 5, and then halfway along, this is 2 more units, is 1, 2, so 7 inches, all divided by our total weight, which is 150 pounds. Okay, so if we take out our calculator, calculate that, so we have 50 times 3 plus 100 times 7 divided by 150, it's going to be we'll round to the nearest hundredth, 5.67 inches. It's going to be about here. Now you might have thought, it's got to be much further, but the reason it's not is because the center of the 100 pounds is right here in the y direction. It's not all the way up here, it's just here. So this is actually, if you think about it, the two centers are right here. This is pulling it pretty far. It just, it's less than an inch because, well, this whole thing is only 10 inches big. So, 0.67 inches. And it's, it's a large amount over this scale. Okay. Now, if we wanted to calculate the center of rotation for this object, this robot, first thing we need to know is we need to know the coefficient of friction for all of these wheels. Now, let's assume these are standard treaded wheels. So if this is wheel set 1 and wheel set 2, both of their mu's are going to be equal to 0.3. Now, when we talked about this last time, I said that we're going to get a center of rotation, and there's going to be some distance from the front set and the back set from that center of rotation. But no matter what those two distances are, they're going to add up to be this length. So this length here is going to be D1 plus D2, and we're actually going to give that a variable L. So we're going to, from that center of rotation, we're going to get a lever effect on both sides of the robot, and we're going to have two torques, so torque 1 and torque 2. And the two torques have to be equal to each other. And we use that fact to help us calculate where our center of rotation is. Torque 1 is going to be equal to our force of friction 1 times our distance 1, and torque 2 is going to be equal to force of friction 2 times d2. And if we look at this, we actually already know that L is equal to 1, 2, 3, 4, 5, 6, 7, 8. So we know that d1 plus d2 is equal to 8 inches. Now I told you guys that for the force of friction 1 is going to be equal to our first normal force times our coefficient of friction, which here is 0.3, and force of friction 2 is going to be equal to our normal force 2 times coefficient of friction 0.3. And what I told you was you just should evenly split our normal force between the wheels. So here, 150 pounds, you would make normal force on this side. This wheel would be, a quarter of that. This would be a quarter. This would be a quarter. This would be a quarter. So it'd be 75 pounds on each side. But that's not exactly true. And what I told you was a little bit wrong because there's more weight on this side because our center of gravity is closer to this side. So the way we actually find our normal force is by taking kind of like a percentage of our weight that acts on each side. So over here, we have, this distance L, 8 inches. The way this works is, for our first normal force, just go down here, it's going to be 150 pounds times the distance, not from the end, but from our wheelbase to our center of gravity. So from here to here. Now for this one, even though it's on this side here, we want to use this distance because there's more on this side. There's a bigger percentage on this side. So we're going to use that distance here. So it's going to be 4.67 inches divided by L, which is 8 inches. And for our normal force 2, it's going to be the same thing, except for our numerator, we're going to use the other side of this, which is 3.13 inches. So our normal force 1 is going to be equal to 87.56 pounds. And our normal force 2 is going to be equal to 58.69 pounds. Now we can plug those back into our formula. In general, you're not going to really have to do this math. We're just kind of going through it as we conceptualize these concepts. So we can plug these back into our formulas up here. So torque, frictional force 1, actually, is equal to 87.56 times 0.3. Frictional force 2 is equal to 58.69 times 0.3. Frictional force 1 is equal to 26.27. Frictional force 2 is going to be equal to 17.61. Okay, now that we have those, we can plug them up here. So we know that torque 1 is going to be equal to this, and torque 2 is going to be equal to that, and they're going to be equal to each other. So 26.27 times D1 is going to be equal to 17.61 times D2. And we can use this up here to help us. So if we just say D1 is equal to 17.61 divided by 26.27, we get 0.67 D2. We plug that in here. So 0.67 D2 plus D2 equals 8 inches. 1.67 D2 equals 8 inches. D2 equals 8 divided by 1.67, 4.79. D1 is going to be equal to 8 minus 4.79. Eight minus answer 3.21 inches. And what you'll notice is that these numbers are very close. Like if we actually put these distances in from here, well, D2 would take us to about here. D1 would take us to about here, so because it's distances from these two. And the only reason that these numbers are 4.67 and 3.13 is rounding error. They're actually going to be the same. The center of gravity and center of rotation are going to be the same here. The center of gravity has an immense impact on our center of rotation. So in general, you're not going to really have to do any of these big calculations to figure out where our center of rotation is, but it's important to know that the center of gravity does impact the center of rotation. You don't just use these formulas here. You can't just use that and assume that our normal force is evenly distributed. When I give you problems like this, I will give you a set normal force acting on each wheel to make it easier. Now, the big reason why we care about these things is this part right here, our torques. Our torques are going to be what we're fighting when we're trying to turn. And if that torque is too big, our motors will not permit our robot to turn, and our motors on our drive base will stall. So on your robots, the ones you built, you don't really have any issues turning. And the reason for this is because the wheels on the robot were very close together. So that distance, this one right here, L, was very small. So if L is small, turning won't be a huge issue. As L increases, so does torque 1 and torque 2. Put a comma here. So does torque 1 and torque 2. Now there are a couple of things that we can do to address turning issues. The first thing we can do is we can reduce our coefficient of friction by doing things like introducing omni wheels. Omni wheels allow you to turn more, but let's say you have a very big drive base, something that's very long, and you can't use omni wheels because the application it just doesn't work for. You have these wheels here. You have to have them, and they have to have a high coefficient of friction, and you can't turn. Well, what can you do to address this? There are a couple of things you can do. One, you can introduce a lower additional drive base in the middle, so an 8-wheel drive with slightly lower wheels. So basically these wheels are always on the ground and these wheels are not. They just kind of interact the ground. When you move back and forth, they tip onto them, but your L will be this distance here. This we call an 8-wheel drop. And then you can also alternatively do what we call a 6-wheel drop. So this wheel is lower than the other two, and the robot will rock back and forth onto one side or the other, and your L will always either be this distance here or this distance here. And because your center of gravity will be, about the center, you're still going to turn about your center with this kind of setup.